Okay. The test will have to do it involves a chain rule protocol. Maybe. I'll post the test on Friday morning when I wake up. So probably 7-ish around there. So 10:05, yeah. So you'll have Friday. Yep, we can do that for sure. We'll have time today. Yep. So Friday I'll probably post it at 7, and I'll give you until Monday night, 10:05, at 11:59 to hand in both homework 4 and exam 2. Okay. So please, hey, oh, you can't be down here. All right, hold on 1 second. Oh, I know. Yeah. So where was I? Yeah. So homework 4, exam 2, 10:05 by 11:59, and I may just take a look at a mini break. So I think I probably will do that. We won't start chapter 13 till next Friday, so you'll have a break from dynamics. It'll give me time to get caught up, get some grading done. Okay, so let's shoot for that. So I'm going to update that Excel schedule. So it'll be kind of a good break. I think we need it. We'll go over number 3. Yep, we'll do that. And Joseph, there could be a chain or a product rule. I won't do product rule, but there could be a chain rule. Okay, I won't have you double. The product rule is definitely a little bit more intense, and the chain rule isn't as bad. Okay, but good question though. All right, we'll go over homework 3 for sure. Let me show you. Let me share my screen here for a second. So I did a couple experiments. The first one I just want to show you is not that one. I'll get to that one. I don't know what I just did. Okay. Oh, whoa, that's laggy. I couldn't see that. All right, so here is, I'm just going to pause it here. Okay, yeah, we can look at problem 5 too. I'll post this video up too so you can see it. It may take a little bit, but I'll do it after class. But what I had baby runners in the picture, I didn't even notice that. So I made a pulley system outside, and there are 6 ropes, okay, attached to a movable pulley system. All right, so up on the top, see this rope right here? This gets pulled over to the left, and there's another pulley system that I pull down over here. So I'm pulling down on this side right here where the mouse is, and these are being pulled up, okay? And what I did was each line or each section of rope will actually move at a different speed. And one of my problems that I put on the one of the videos that I put up about blowing your mind kind of thing, I think that's the name I titled it, I show you how to calculate the velocity at each section of those ropes. And I think it's good for you just to visualize what would happen. So I put different color zip ties on each section of the rope. At the bottom, where my mouse is right now, that's orange. That rope is hooked directly to the rope I'm pulling. So that one's going to move up the fastest. Okay? And then you have this purplish violet color here. You have this blue zip tie right here. Okay, on the left. This is also a blue zip tie right here on the right. However, that rope is the last section, and that does not move. Okay, that does not move at all. Then at the very top, you have a green zip tie, and you have a yellow zip tie. okay? So those two are going to go down. These three on the left at the bottom will go up, okay? And hold on, let me see if I can upload it in week 5 as we're going through this, okay? I'll just do it right here. I was going to do this, but between statics and dynamics, but they ended up having a big old diaper. Let's see, I don't know how long it'll take, but I'm uploading it in week 5 right now. So in reality, if I'm pulling down on the left side with a known acceleration, okay, say that's constant, then the bucket that or even that pulley system right here where my cursor is, that will move up at a rate of 6 times less, okay? And so what I did was I put sensors, 2 different sensors, one in the bucket and one where I was pulling down, and I looked at data for actually 15 different trials. Okay, so I try to pull down with a constant velocity, and I compared the accelerations, and I'll post some of this data too for you to look. But I got a ratio of around 6.3. Okay, so it was pretty close to 6, but it was pretty cool to see that. All right, well, let me hit play and see. I don't know if it's going to be laggy. It might be laggy. Yeah, it's pretty laggy. I'm not sure why it's so laggy. But as you can see, let's see here. You can kind of, as I go to the right, you notice the orange zip tie moves the fastest, okay? And the other zip ties are kind of in between. All right, and the blue one at the bottom here, there we go. That wasn't too bad. Try to do it here. So I thought this was good. Usually I have this set up in the classroom. Hold on, I gotta move Render back. Hey. No. I said no. I said no. Here. Hold on. Okay, so that video should be up in week 5 if you want to download it and look at it later. But hopefully you see that depending on the rope section, it's going to have a different speed. Okay. So, so I just wanted you to see that because it's kind of like, oh, sometimes students don't think of that. Okay. Does that make sense, everyone? Okay. And then I don't know if this might be laggy too. Oops, hold on, I downloaded this already. So this one I want to look at and analyze too, okay? I never did. Okay, that's fine. So I had my camera record, and then if you notice, I have my computer. I'm just going to pause it right here. So here's the computer. And I have 2 sensors. I have a sensor that measures acceleration on the car here. All right, that's going to measure acceleration in the X, which is this direction along the boards. Okay. And then you see the green bucket. That has another sensor, acceleration sensor, and it's going to measure the Z direction acceleration. Okay. So what's going to happen is this car is going to pull this rope, which is diagonal, okay, which is right here along my mouse, all the way up, and there's a pulley system here, and it goes down and wraps back up, okay? So there's 2 sections of rope on this movable pulley system that's moving the bucket, all right? And so I floor it, okay? And I'm going to analyze this for you. We can use basically the math And we can figure out the velocity relationship and eventually find accelerations, okay? And next chapter, we can use those accelerations to figure out the tension in the rope if you need to like size that rope, okay? Understanding how to do the position coordinate equation and how this all works is key, okay? Now I did this, I think I did 20 different trials with 3 different cars, and I finally found this last one to be the best one, okay? I don't know how laggy that is, but I'll share the link too. I don't think it's too bad. Okay, and then it popped off, and you can actually see in the data that that's acceleration. Okay, so let's just look at this. It'll take maybe 10 minutes, and then we'll look at the homework. Okay, because this will help. This is a good review too, because this was actually a test question last year. We'll go to 301 on week 5. Okay, and then day 2, right? Runner in the bucket. Okay, all right, so here's a cool little sketch. Here's the ground. Here's my car. Fancy car, I know. And then here is the pulley systems. And I think I attached it, shoot, it's okay. I think I just attached it here, that's fine. And here is the bucket. And it's initially down here, okay? And we're moving this way. And let's pick the height. Let's do that in orange, from the top of the bucket to roughly right here. So the way this problem was described, and I'll get it here. This one, it's week 4, let me check. I'm not sure if this is the notes. Okay, this is the notes. All right, that's fine. It's okay, I'm not sure where I put it. Basically, what happens is I tell you that this truck is accelerating at a constant rate, all right? And want to find the velocity of the bucket as it goes up, okay? So this is, again, dependent motion. So what we need to do is we need to define the length of the rope. So I'm going to define basically right here my datum. And I'm also going to define a datum this way. So you can do 2 different datums like this as long as they're kind of related to kind of each other, kind of touching each other. Okay. So this bottom datum to the car, I'm going to label it as SA. So the distance the truck is away from that datum And I'm going to label these two sections of rope SB. So far, is everyone, is this making sense, what we're doing? Questions? Okay. So basically, this section of rope changes, this section of rope changes, and this section of rope changes. So this length is basically h squared plus SA squared. So the length of the rope is we have 2SB plus the square root of h squared plus SA squared. Questions? Does it make sense?
Yeah, it makes sense. This is similar to problem 3.
Yeah, probably, yes. Yep. Okay. So now what we need to do is just take the time derivative of this position coordinate equation. So we have 0 equals 2VB plus, I'm going to do the, I'm going to write this down and then we'll do it over on the right because it's the chain rule. It's going to be 1/2 h squared plus SA squared to the minus 1/2 times 2SA times VA. So how did I get that? Well, I called y h squared plus SA squared to the 1/2. If I want to find the derivative of y with respect to t, and t is not directly in the y equation, but we know a variable in there is a function of time, you have to use the chain rule, which states dSA, dy dSA times dSA dt. So you take the derivative of the y as a function of SA and then multiply by dSA dt. That is the fundamental chain rule. So this green term right to here is this derivative. Is the derivative of y with respect to, you just multiply by 1/2 and you subtract 1 and then take the derivative of the inside. And then this orange one is just dSA dt, which is just the velocity. So what we end up getting is VB minus SA times VA over 2 times h squared plus SA squared. Oh, one more time. the tunnel. Let's see if we crawl through it. Questions? How would we find?
I do have one question. The
Yeah.
In the VB equals like the last one, the 2 on the bottom, the 1/2. Wouldn't that be canceled out by the 2 SA?
No, because you got the 2 here. 2 VB. The 1/2, these do cancel, but you have to divide by 2.
Okay, yeah, I got it.
Yep. Yep. Other questions? Okay. How do we find VA and SA, which is the velocity and the position of the car? Which direction is the car going?
To the right.
To the right. What type of motion is it that you think it's going in one dimension? Positive? Okay, so what stuff did we start with in this class? Remember? Was it curvilinear? Or the other one that started with an R? Yeah, rectilinear. Yep, perfect. So it's straight motion. If A is constant and it starts from rest, then these are the equations that you can use. So that's how you can find velocity and position. So a few more minutes and then we'll get right to the homework, okay? I am going to make my other computer presenter and show you some graphs, okay? Which is pretty cool. Questions why I'm pulling this up? And I'll go back to this here in a second. Let me stop sharing and let me share this. One screen one. Oh my God, he's actually going through the tunnel. No way. All right, so here, look at this. A little noisy, but let's look at this, okay? This graph that's right in front of you, I'm trying to make it bigger, but it won't let me, is accelerations. The red is the bucket, so Z direction, and the blue is the truck, okay? Or I think I have it flipped. Oh, crap, I think I have that wrong. Blue should be the bucket. Let me fix that. Right, give me a second. I'll rerun these. So while these are rerunning, if you know accelerations as a function of time, how do you find velocity?
Integral?
Yeah, or it's the area under the curve, right? Yep. And that's what I did. So I just used what the trap Z command, but you basically find the area under the curve. Okay, so there we go, that's right. So the blue is the bucket accelerations from the sensor, and the red is the truck accelerations. So over here on the left graph, I'm gonna move the legend here, but it won't let me. we have velocities versus time. Don't worry about the black and the magenta. Those are extra things that I put on there. But if you notice, there we go. Here is the red, so that's the truck. That's not too bad. So it kind of isn't quite linear, but it's pretty close. The dotted red is a linear fit to that data. Okay, so it's not relatively too bad. And the blue is a linear fit that's dotted to the bucket bucket velocity. Okay, because the slope of this graph gives you your acceleration. So we can kind of assume that it's constant. So again, we have accelerations versus time. If we find the area under each dot, we can find velocity at that time. And if you do a linear fit, you can see that it's relatively linear, not great, but it's relatively linear. And the slope of that line is your acceleration. And then if you plot position versus time, if the velocity graphs are linear, then these should be to the second order. Okay. So here's the truck, here's the bucket. And what I did is I made sure that the endpoints are relatively close to what I would actually go out there and calculate. So I actually put these in their final positions and measured with a tape measure. And these numbers are really close. Like the bucket went up almost 2 meters, and the truck went just about 4 meters. So this is a little farther. Okay. So these are the actual data that I calculated. And I used the equations I just showed you down here to see if they match. And they do. So at a time of 1.4 seconds, which is right, the bucket should be roughly around 2 meters per second, which it is. Okay. So the point I'm trying to make is I did experiments. I showed you we can analyze the data and look at the theoretical equations, and they should match relatively close. Okay. I'll post this code with the data, so if you want to run this, you can look at it. But I hope this makes sense. Does it? How we use dependent motion, how we have some sensors, how we can kind of relate all this stuff together. Does that make all sense? Does that make sense, everyone? Okay. So let me put this as a note for me. I will post video on car and pulleys and the .mat.m file with data. So you can mess around with this if you want, okay? All right, I'm going to stop sharing and let's go in homework 1, okay? Is that what you want? Or homework, problem 3, is that right? 3, yep, okay. Hey, bud, what are you doing? I have to put you back over there? Okay, so I'll keep that there in case you need to finish that. And let me get the homework up. Give me a second. Dependent motion. I'll pick up both of these. Hey, what are you doing? Guess you're fine for right now. All right, problem 3. Oh, okay. Yep. All right, so you should have this for the position coordinate equation, right? Is this what everyone has? XC plus XA squared plus 4 squared? because it gives you the basically what it is we have a crate. It's very similar to what we just did. And they tell you that this distance is XC, this distance is XA, and this distance from here is 4 meters. Cool. All right, so let's take the derivative. So we get VC plus 1/2 XA squared plus 4 squared to the minus 1/2 times 2XA times VA equals 0. Hey, hold on. Probably the time. So this, let me write this a little neater. I'm sorry. XA 4 squared minus 1/2 times VA. This is exactly what we just did. Okay, so do what we just did to that. Now, this is the pain in the butt part. This I will not test you on, but it's good to practice this in the homework, okay? I'm going to rewrite this. Yeah, I'm going to rewrite this as XA. Actually, I'm going to do this. I am going to say Y times XA times VA equals 0. So Y is XA squared plus 4 squared to the minus 1/2. The 1/2 and the 2 cancel. And we have to take a time derivative of this big old monster. So let's start. First term's easy. AC. Plus, we're going to take the derivative of the first function with respect to time, and we're going to multiply by XA times VA. Then we're going to add the derivative of the second term with respect to time times VA times Y. Then we're going to add the derivative of the last term with respect to time times XA times Y. So you're doing, this is the product rule, okay? All right. So we get AC plus the derivative of Y, which is over here. This is Y with respect to time. Okay, so it's dy dt going to be dy dxa times dxa divided by dt. So you're doing the chain rule again. So this becomes, let me do this term in light blue. So this becomes minus 1/2 XA squared plus 4 squared minus 3/2 because you subtract 1 times the derivative of the inside, which is 2XA. Now, dxa dt is this purple one, which is just VA. And then you have to bring down XA times VA. This term, and that term. So this entire section here is dy dt. Questions on that? Pretty groovy, huh? Pretty derivative? Come on, you gotta laugh. This is good stuff. You're applying your math that you never knew you would apply. And the crazy thing is, next time you lift anything with pulleys, or say you want to pull down a tree with a truck, do these calculations first so you don't have a rope that's going to snap and kill somebody. I haven't seen that happen, but I've seen the rope snap before. Okay. All right, let's keep going. Then we're going to add dxa dt is just VA times VA times this puppy. And then I'll do it in blue, plus I'll do this term. dVA dt is just AA times XA times XA squared plus 4 squared to the minus 1/2. On Friday, I can help you with, we can review, and I can help you with problem 4 too. Okay. So problem 5 is very similar to this too. It's good practice for math. Okay. Good product rule. Now, did that answer your question, Jesse?
Yeah, Dad, that's exactly where I was stuck.
Yep. And who else said something about problem 5? Joseph? That's you said you did problem 5 like this? Yeah, right there. I did problem 5 the other day, and it was a little tough. There you go. Yep. So hopefully you see now, hey, don't hurt yourself, where the applications of math now come in, right? Look at how you would think this problem is just 2 ropes, right? Just a pulley. But it gets very, very tricky. Okay, other questions? Hey, don't wreck that. I guess you can have that. Anybody do problem 4 yet? I would, if you haven't done problem 4, I would do that before Friday. Okay, and we can review that one Friday. That's a really good question to make sure you really understand how these datums and kind of things are making sense. Okay. Actually, I got time now. Why don't I help it?